Last topic here in section 12.4 on the cross product is how do we use the cross product to compute volumes and areas of certain geometrical figures. How do we compute these using cross products? And the things that we're going to compute going to be volumes of parallelopipeds. I'll tell you what that is in a second. And then areas of parallelograms and triangles. So I'm going to start off with areas here. So suppose that, let's draw some axes here. Suppose that we have, here is vector v, and here is vector w. So I'm drawing them so they're both coming out of the origin here. We can always translate that. And we should think of these are floating around in 3 dimensions. Well, we can draw a parallelogram that is spanned. So parallelogram that is spanned by v and w here. So any two vectors, both coming out of the origin, let's assume they're not parallel with each other. Any two vectors, they're going to define a parallelogram in this way, where you just translate v up here, translate w over here. This is going to be our parallelogram. And as it turns out, there is a very simple formula for the area of this parallelogram. And the area is, well, I told you that you have to take the cross product, and that's all you do. Well, not quite all you do. If you take the cross product, you get a vector answer. Area is a scalar. So how do we turn a vector into a scalar? It turns out all we have to do here is take the length of the corresponding vector. So how do you find the area of this parallelogram? Just take the cross product of those two vectors, take the length. Sometimes I can ask you about the area of this parallelogram. Sometimes I will ask you about the area of this triangle. How do you find the area of that triangle? Well, the area of the triangle is just half of the area of the parallelogram. And so all we literally have to do is take our previous answer and divide it by 2. Okay, so let's see an example of this. Let v be the vector 1, 4, 5. Let w be the vector -2, -1, 2. Find the area of the parallelogram spanned by those two vectors. So we know all we have to do is take the cross product of v and w and take the length of that. So I hat, j hat, k hat, 1, 4, 5, -2, -1, 2. And so what we end up here is I hat times 8 minus -5 is 8 plus 5 is 13. J hat times negative j hat times let's see here, 2 minus -10 would be 2 plus 10 is 12, plus k hat times -1 minus -8 would be -1 plus 8 is 7. So 13 I hat minus 12 j hat plus 7 k hat. So we found v cross w, so the area parallelogram is equal to, the magnitude of this is equal to 13 squared plus -12 squared plus 7 squared, and my notes say that that is the square root of 362. And that it's okay to just leave that as our square root. And square root of 361 is 19, so this is ever so slightly bigger than 19. If, to finish off this example here, if I had instead asked for a triangle, I could have asked that question instead. Make sure you pay attention to which question I'm asking here. Area of the triangle would just be square root 362 divided by 2. Okay, so that is the area calculations, areas of parallelogram and triangle. The next thing we have to do here, I don't want to show that next slide quite yet, so, okay. You know what, let me show this one. This expression here, this is called the triple product. This is called a triple product here, or the triple scalar product, sometimes called the box product. So if I say to you, what's the triple scalar product of u cross v, parentheses, dot product w? As it turns out, the simplest way to compute it is through this determinant, where you put the entries of u in the first row, you put the entries of v in the second row, you put the entries of w in the third row, and this is going to be, let me tell you this here, so u cross v dot product w, the absolute value of this, assuming, you know, we want to make sure that this expression ends up non-negative, is the volume of a parallelepiped. And so a parallelepiped is the 3D analog of a parallelogram. And so, you know, I have some vector u here, some vector v here, some vector w here. So the idea is, it's like a tilted, you know, off-center, a little bit off-kilter prism here. So how do I draw this? Okay, so there's like the base of our parallelepiped, and let's come up here and draw, you know, some more sides to our parallelepiped and connect up a bunch of things. So it's like a cube, you know, it's like a rectangular prism, just kind of, you know, slanted off center, because, you know, not everything here we're assuming is orthogonal to each other. So this triple scalar product that we compute, I mean, you can certainly do the the cross product first and then do a dot product, but it's easiest just to go straight to the 3x3 determinant formula here. Take the absolute value of this, it gives you the volume of this parallelepiped. Okay, so here's example, find the volume of this parallelepiped determined by u, v, and w. So I'm not going to redraw the picture, but we should, you know, here's u, here's v, here's w. I gave you, you know, what u, v, w are, and we calculate out the vector, the triple scalar product through this formula and take the absolute value if necessary. So this is going to be, so u cross v dot product w is going to be, let's put the entries here for u, 1 to -1, then -2, 0, 3, and then 0, 7, and -4. Okay, and so now we just have to calculate out this 3x3 determinant. So it's going to be 1 times cover up, you know, the determinant that you get here, times 0, 3, 7, -4, minus 2 times cover lows up this determinant, -2, 3, 0, -4, -2, 3, 0, -4, plus -1 times cover lows up, negative 2, 0, 0, and 7. So if we crunch this out, this one is 0 minus 21 times 1 is negative 21. This is going to be 8 minus 0 is 8 times negative 2 is negative 16. And then plus negative 1 times, that would be negative 14 minus 0. So that's plus 14. And this gives us negative 23. Volume can't be negative. Volume can't be negative. This is why we have absolute values here. So volume equals the absolute value of U cross V dot W is equal absolute value of negative 23. The volume of this is 23 units. Okay, so that is a nice little use of the cross product to do a couple of different types of calculations.